Imagine a trampoline, not the kind you bounce on, but a vast cosmic one. This is how Albert Einstein taught us to picture the universe. This trampoline is space-time, a blend of space and time. Massive objects like stars and planets sit on this trampoline. They create dips, warping the fabric of space-time around them. This warping, my friends, is gravity. General relativity beautifully explains the motion of celestial objects. Planets orbit stars, galaxies swirl, and black holes consume matter, all guided by the contours of space-time. But there's a subtle mystery lurking within this elegant theory. Consider an apple hanging on a tree. It's perfectly still, yet it's undeniably under the influence of Earth's gravity. If gravity is just the curvature of space-time and the apple isn't moving, what's pulling it down? The apple, though seemingly at rest, is actually in constant motion through space-time. Remember, space-time is not just space, it's space and time interwoven. The apple may be stationary in space, but it's moving through time. This is where the mystery deepens. If the apple is already moving through space-time, why does it experience a downward pull? Why doesn't it just continue along its space-time trajectory? This question, while seemingly simple, exposes a profound puzzle at the heart of our understanding of gravity. To solve this puzzle, let's explore a mind-bending idea. What if massive objects don't just warp space-time but actually consume it? Imagine space-time as a cosmic ocean, and massive objects as cosmic whirlpools. These whirlpools, these massive objects, don't just distort the flow of space-time around them. They draw it in, consuming it. This consumption creates a current in space-time, pulling everything towards the massive object at the center of the whirlpool. Imagine our apple again. It's caught in the current of space-time flowing towards the Earth. This continuous consumption of space-time is what we perceive as the downward pull of gravity. The apple isn't just moving through time, it's being pulled along by the flow of space-time itself. This concept, while radical, elegantly explains why objects at rest still experience gravity. They are not static. They are being carried along by the invisible current of space-time being consumed by the Earth. The apple, held by the tree, resists this flow, creating the sensation of weight. Section 4. Newton's Legacy: Finding Harmony Between Old and New Ideas. This idea of space-time consumption might sound strange, but it surprisingly aligns with Isaac Newton's law of universal gravitation. Newton's law states that every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. How does space-time consumption fit into this? The more massive an object, the more space-time it consumes. This creates a stronger current in space-time, which translates to a stronger gravitational pull. This aligns perfectly with Newton's observation that more massive objects exert a greater gravitational force. The distance part of Newton's law also fits. As you move further away from a massive object, the flow of space-time towards it weakens. The current becomes less intense and the gravitational pull decreases. This explains why the strength of gravity weakens with distance. So, while Newton described gravity as a force, and Einstein redefined it as the curvature of space-time, the concept of space-time consumption provides a bridge between these two ideas. It offers a way to visualize and understand the mechanism behind this fundamental force that shapes our universe. Section 5. Gravity's Elusive Messenger: The Boson versus Space-Time Consumption. In the world of physics, forces are often carried by particles. For instance, the electromagnetic force is carried by photons. Some physicists propose that gravity, too, might be carried by a particle called the graviton. The graviton, however, remains elusive. Despite decades of searching, we haven't found any experimental evidence to confirm its existence. This leads us back to the idea of space-time consumption. This concept offers a compelling alternative. Instead of relying on an undiscovered particle, it explains gravity as an inherent property of space-time itself. Massive objects, by consuming space-time, create the gravitational currents that govern the motion of matter and energy. This doesn't invalidate the search for the graviton. Finding it would be a monumental discovery. However, the concept of space-time consumption provides a framework that doesn't require the graviton to explain the force of gravity as we experience it. Section 6. A Universe of Possibilities: Exploring the Implications of Space-Time Consumption. The idea of space-time consumption is still in its infancy. If massive objects are consuming spacetime, what happens to it? These questions take us to the frontiers of physics. It might offer insights into black holes, dark energy, and the universe's expansion. Keep exploring the cosmos.